at a high level what this whole program will be about during the fall. Thanks. Okay, so yeah. So foundations of data science. So data science is a term that's a catch-all term to describe, say, the intersection of applied mathematics, statistics, and computer science. And some of the goals of this program are to bring together researchers working on the algorithmic, mathematical, and statistical foundations of data science. And we have emphasis on the following topics: dimensionality reduction, numerical linear algebra, optimization, probability in high dimensions, sparse recovery, compressed sensing, statistics, inference and causality, and robust statistics, streaming and sublinear time algorithms. And the goal is to strengthen connections between these areas and to get different people to talk to each other. Okay, so a lot of different communities are working on these problems from different perspectives, and we'd like to understand the important problems and the assumptions being made in these communities. So let me give you a rundown of the bootcamp schedule. So the goal of the bootcamp is to provide a sequence of tutorials to get everyone up to speed on the techniques used in this area. So the first talk will be given by Ravi Kannan from Microsoft Research. So he'll give an overview. He'll, based on his Foundations of Data Science book, it's a great book, he'll give an overview on techniques such as high-dimensional geometry, concentration inequalities, Gaussian densities and mixtures, singular value decomposition, Markov chains, rapid mixing, streaming algorithms, and some randomized algorithms for matrices. So he'll give the first two talks this morning. Then I'll give the next two talks this afternoon on dimensionality reduction to obtain fast algorithms for linear algebra problems, things like regression, low-rank approximation, robust variance, clustering, tensor problems, etc. Tomorrow, Ken Clarkson from IBM will continue dimensionality reduction. He'll look at importance sampling for different objects, in particular things like subspaces, where you use leverage score sampling. He'll discuss this and connections to other fast dimensionality reduction techniques like the subsampled randomized Hadamard transform. Following those talks, Rachel Ward from UT Austin is going to give us a tutorial on first-order stochastic optimization. So she's going to cover stochastic gradient descent, applications to deep learning, importance sampling to improve convergence, and there are many different parameters in this landscape. She'll talk about things like adaptively choosing step sizes, etc. Then we'll have Michael Mahoney, who's here from UC Berkeley, talk about leverage score sampling again. He'll try to connect two different talks. Ken's talk on leverage score sampling for dimensionality reduction, fast algorithms in linear algebra. So those guarantees of leverage score sampling are quite a bit different than those used for, say, importance sampling in stochastic optimization. So it'll also tie in well with Rachel's talks. So he'll give trade-offs between those. And then we'll have Fred Rusla from University of Queensland talk about second-order optimization methods and stochastic variance. Okay, so efficient Newton-type algorithms for convex and non-convex optimization, and a comparison between first and second-order methods. Next, we'll move into a more statistical flavor of talks. Will Fithian here at Berkeley will give the first talk on statistical inference. And you can look at this as a crash course in theoretical statistics. So he'll talk about things like estimation, hypothesis testing, confidence intervals from a frequentist perspective, Bayesian inference, and some classical asymptotics. So that will kind of set the stage for two remaining talks. So Santosh Vempala from Georgia Tech will talk about high-dimensional phenomena, for instance, distribution of mass, log concavity, extremal properties, different versions of Dvoretzky theorem, concentration of measure, and isoparametric inequalities. Following that, Ilias Diakoniklis from USC is going to talk about robust statistics. Okay, so there's a lot of exciting work, both by Santosh and Ilias and others, on obtaining very efficient algorithms for mean estimation and covariance estimation of a Gaussian distribution in the presence of extreme outliers. So there are sort of classical methods that do this inefficiently and very recent efficient methods. Finally, on the last day, we'll have 2 more tutorials, one by Ilya Razenstein from Microsoft Research. He'll talk about nearest neighbors, so a lot of recent exciting developments there in high dimensions. So he'll first give an overview of locality-sensitive hashing, or LSH, and then move on to some of the provably better algorithms based on data-dependent hashing. That'll be the first part of his talk. In the second part, he'll talk about very recent exciting work on extending this to non-Euclidean geometries. And finally, the last tutorial will be given by Michael Kapilov from EPFL, who will talk about the data stream model. This is a model for processing massive amounts of data with low memory, and you want very high-speed algorithms. So he'll be talking about problems such as estimating statistical moments, finding frequent items, algorithms for mining graphs in a stream. And so that's all. Let's go ahead and get started with Ravi, who will give the first talk. Thanks everyone for coming.
So thank you all for coming. I should start by saying in every organization committee, there's somebody who gets a little bit of a free ride and somebody who does a lot of work. I'm an example of the former. I must thank David for being the latter. He has put in enormous amount of work. So thanks to him. Now, when we were discussing the bootcamp, the meaning of the word bootcamp is that you present basics that cover a lot of stuff. We sort of decided to stick to that definition a fair bit. We'll have some new results. Especially my talk will be really basics. It's not my intention. I mean, this is not a research talk, so it's laying the grounds for other talks or setting the tone and language and so on and so forth. But I do hope, I mean, a lot of you are, of course, going to be experts and will know a lot of this stuff. But I do hope you see at least a few new ways of looking at things. Not new, maybe unusual. They are all classical, really, but unusual ways of looking at things, perhaps. But it'll be familiar to all of you, and if I bore some of you, that I'm achieving my aim. So foundations of data science, recap of the basics. First, I'm going to start with concentration inequality. I mean, good old concentration inequality, except I hope you'll see something slightly unusual here. Again, not new. I mean, this is just of pedagogical value. A lot of this is from a joint book I'm writing with John Hopcroft and Avram Blum. Is downloadable from John Hopcroft's webpage. So, except this proof is not there, but otherwise many things are there. So, first let's look at sums of independent random variables with mean 0. We want to show that the sum x, oh, I didn't say that the x was the sum, I should have. Sum x is concentrated around the mean, right? And Hoeffding-Chernoff, which we use a lot, of course, the first step is to say that probability x greater than a is less than or equal to the expected value of e to the lambda x minus a for any positive lambda. So moment generating function. That's good. And it gives you very elegant proofs because this is a nice function. So you upper bound that. These are what you might call exponential moments as a function of lambda, and then take the minimizing lambda, right? That's what we do in Hoeffding-Chernoff. But of course, this assumes that the exponential moments exist. They're finite for all lambda. Well, they don't have to be for all lambda, but they must be at least for the minimizing one, minimizing lambda that you use, right? Otherwise, this doesn't make sense. Okay. Now, here is, I mean, it works very well for Bernoulli random variables. We often see this proof, of course. The upper bound on the exponential moment for Bernoulli's follows just from the absolute bound. Each of the xi's is absolutely bounded by 1, and that gives you bounds on the exponential moment. I can play around with calculus and get the best bound. So, should this be all that we learn or teach? I'm going to suggest perhaps not. I'm going to let's look at some distributions in data science or any field, right? Gaussian, of course, comes all over the place. Gaussian density does have all exponential moments because you have x squared fall off there, and e to the lambda x is fine, right, for any positive lambda. Exponential moments for positive and negative x, maybe you have that, c is a normalizing constant. Here already, not all exponential moments exist. If lambda is much greater than 1, you get into trouble, right? Things blow up. If lambda is small enough, things exist. So you have to be careful about the minimizing lambda. But indeed, you all know that in modern data, one bandies around this phrase a lot, that power law distributions do occur. So power law means the kth order power law, for example. I mean, this is not the only, there are generalizations, but you have a normalizing constant divided by x to the k for x greater than 1. Okay. Certainly no exponential moment exists, but even, of course, the k plus k minus first and higher moments already blow up, right? The integral is infinite. So you cannot apply the moment generating function method that I showed you, or the Bernstein method it's called, that I showed you in the last slide, right? You've got to do something else. Now, what we do, I want to put up one more. Chi-squared is the square of standard normal. Here some exponential moments exist, but not all. And chi-squared is used in a lot of things. In particular, a little bit later, I'll show you Johnson-Lindenstrauss. I'll recap Johnson-Lindenstrauss, and the proof uses the fact that sums of chi-squareds are concentrated. So what do we do in a lecture or a course often is, whenever we encounter one of these, we go and by hand prove each one individually, right? What I would like to tell you is that there's one general simple concentration inequality, and all these will be corollaries. Again, I don't think this is new, although I don't have a reference, but I mean, I'll give you a proof. And the idea is just simply go back to classical, good old finite moments. Finite moments means kth moment for some fixed k is for moment generating functions. Historically, in probability, of course, finite moments were around before perhaps the exponential moment, the Bernstein method. But the Bernstein method is so beautiful because exponential factors nicely that it captured all the attention, and perhaps one doesn't see so many proofs based on finite moments, but they are certainly classical. So here you'll see one. And I just want to recap before I do that. If r is an even positive integer, the finite moment method, if you will, just says that the probability that x is mean 0 greater than a is bounded by this. This is just Markov inequality applied to the non-negative random variable x to the r. Okay? And then we need only prove upper bounds on e expected value of x to the r, the rth moment. And the nice thing is it exists more often than the exponential moment. Okay? So as a plug for using finite moments in teaching, it'll be good to do that, just because all of these don't have to be proved by hand separately. And so I'm going to state one particular theorem, and this theorem does imply everything that you want, and it's fairly simple to state, and I'll give you some intuition. The hypothesis is these are independent, mean 0, that's the sum, the variances of sigma is squared, and the sum of the variances is the variance of x, of course, right? Is sigma squared. Okay. S is some positive integer. I'm going to deal with the s moments, and there is a bound. The thing I'll show you here does not work for very large deviations, as indeed Hoeffding-Chernoff also has to be modified. The quadratic fall-off doesn't work for large deviations. And I'm going to assume something that looks strange. The expected value of the rth moment, the rth moment of individual xi, is at most the variance times r factorial. This r factorial is, in a sense, the best you can put there. I won't argue that, but I'll argue that things work with r factorial. And the conclusion, which I will interpret verbally in a few minutes, but may look strange first, but let me just tell you, the conclusion has the power of r is r over 2. That's important. and the power of the standard deviation sigma is sigma to the r, which is natural, correct scaling. Okay. That's the conclusion. And this is true for up to the nth moment if you assume nth moment bounds to start with. You can't expect more than that. Right? So I will interpret this verbally in a minute, but first that implies the usual bounds you see. That probability is greater than a is a squared over sigma squared. Sigma is the variance, and a squared over constant times sigma squared is what you would get if you had a Gaussian, right? And central limit theorem tells you that's what you're going to get. Okay, so here's an interpretation that'll be good to remember. This strange looking quantity is just the moments of the Gaussian with the correct variance. If you take a Gaussian with variance sigma squared, the moments look like that. All moments are bounded there and they look like that. So a verbal statement of this that's good to remember, and it's natural, is that if x has sub-Gaussian moments, the conclusion is x has sub-Gaussian moments with variance sigma squared. Sub-Gaussian, I just mean that the c is different from this. This c is not necessarily 2. You can get better constants here. Okay. So again, it's what you would sort of expect from central limit theorem, right? That sums of independent random variables, you should get Gaussian density at the end. And this says that you get Gaussian moments. You don't have all moments, so you don't get Gaussian density, but you get Gaussian moments. Yeah?
There's a literature where people talk about sub-Gaussians and sub-exponential random variables. Is this the same thing, or is it different?
The difference here is I'm only assuming finite number of moments, and I only can conclude something about finite. Sub-Gaussian people mean the distribution, the density is e to the minus x squared over.
Is your sub-Gaussian their sub-Gaussian?
I just mean the moments are sub-Gaussian here.
Okay. Oh, okay.
So their sub-Gaussian is the entire distribution. By the way, that's anyway not true for Bernoulli's. For Bernoulli's, when you have large deviations, you don't have quadratic exponential follow. Yeah?
It doesn't seem like the theorem is giving you very much, because this is only for a between 0 and sigma squared. And if you plug in sigma squared, then you get 1.
Yeah. So it is true that it doesn't work for very large deviations, right? There is a modification that does work, but this is a simple proof and simple statement. And in fact, Herfting-Chernow is often stated with only bounded deviation. So as I said, I mean, this is good old moment method, and should be folklore, except I haven't found a reference. I haven't looked very in a very detailed manner. I'll give you a proof. I mean, this proof is short and teachable, as short as Herfting-Chernow, basically. Okay, so everybody see that? Okay. So only up to the s moment assumed, and okay. So I'm going to do one slide of a proof idea and a couple of slides of the proof. Bear with me. If you don't want to hear it, you can close your eyes. You'll come back to something. It says that actually in the slides you'll see. But okay, something is I'm allowed to do in a bootcamp, assuming a simple proof. Yeah. So this is just to demonstrate that look, using moments is no more sweat perhaps than using exponential moments, right? So you do a multinomial expansion of this. So let's just choose R1 through Rn. These are the exponents of the xi's, and you get that, right? One first key idea in all these proofs, this is not just peculiar to this proof, is terms where one of the xi is raised to the first power go away because the expected value of each xi is 0. All odd powers don't go away. You can, if the x is symmetric, all odd powers will go away. The proof is even simpler. But now at least the first power goes away. So we are left with at most r over 2 non-zero ri, each at least 2. Okay. And so we take those terms, and I conveniently put an ri factorial in the bound in the hypothesis, so that cancels out. And now you have to worry about the combinatorics here a bit. The proof actually has mostly combinatorics as opposed to the Bernstein method. The number of R1 through Rn which have support a particular set of non-zeros of cardinality T, the number of those only depends on T, which is by symmetry. So we are reduced to the same coefficient for each T of cardinality T. We sum over all sets of this thing, product of this thing. And this is, again, I said another key idea, but this is really a bread and butter of combinatorics. If you're using generating functions, for instance, you see this. This is less than or equal to that. You can just get that. That gives you the proof. This was the proof outline. The details, again, basically just going through the outline one more time. I'm going to use the fact that it's a boot camp to dwell on something simple, as I said. Sorry if I'm going to bore some of you. You can close your eyes, right? So I expanded this. I should mention that we are using independence, of course, to say that it's a product of the expectations, right? And this use is the same as the moment generating function method. Also, it's a product. Ri are non-negative and sum to R. If any Ri is 1, it vanishes. We saw that. There are at most R over 2 terms. And all the association of brackets with terms happens in this permutation coefficient, right? Then we get, I'm just running over the same proof again, then we get this, this is just that, and the Ri factorial and this cancel out. And then we group terms by the number of non-zero Ri, which we call T, and let T be the support, then you get that. R of T is the number of Ri which have support T, right? Support T, and the sum is R. By symmetry, R of T depends only on the cardinality and not on T. And a little combinatorics bounds that. Okay. And so we can move that term out and you get the simple sum over all T. And that is at most that. We said that. Now I'll tell you why. That's because if I expand multinomially this thing, all the combinatorics in the multinomial expansions, then for each support T, exactly this term appears T factorial times. There are other terms where sigma's higher powers occur, but we don't care. They're positive.
So Ravi, are we replacing some higher moments by just the second moment in that expression there, or what happened? I mean, why did we get only the support?
Why did we get, sorry?
Yeah, why did we only get the dependence on the
only the sigma I squared. Yeah. But there is a Tth power. So you do end up doing higher moments, right? But we had bounded higher moments by sigma I squared.
By sigma I squared, okay, right.
Yeah. And that turns out to be convenient. And the little calculus says that the R over T term dominates, and therefore you get that, and then you use Stirling to get this. Okay. I don't have to remember everything, but please remember that we got Gaussian moments the same as a Gaussian. Herfting-Chernoff follows in this form. As somebody raised a question, for larger deviations, this is not the case, right? For epsilon between 0 and 1, Herfting-Chernoff has an epsilon squared there. That follows. Right? Why is that? That's proved by showing that the hypothesis is satisfied by Bernoulli random variables. And in fact, it's set up for Bernoulli random variables. If xy is 1 with probability pi, the variance is roughly pi. There's 1 minus pi, but okay. And for any r, expected value of x to the r is pi. So we don't need the r factorial term. Gaussian annulus theorem. This is going to be important for Johnson-Linus-Strauss. Again, a standard theorem. And again, in a course or something, one gets to this, says, oh, well, I can prove this by hand. Of course you can, but this follows from this, right? So if you have independent random variables, normal 0, 1, and you take the sum of squares and the square root, the length of the vector. Now, if you have n of these, this length squared should be concentrated around n, and length should be concentrated around root n, and this says that it doesn't deviate too much from what it should be. And what this says is that most of the mass of the Gaussian lies in an annulus of constant width around radius root n. Okay? That's why I call it Gaussian annulus theorem. The annulus size is different for different distributions. For uniform on a sphere, it's a different width. But this is Gaussians here. I say that. If you have uniform density on the ball, the annulus is smaller, it's 1 over n. But for Gaussians, it's 1 over root n, right? That's a ratio. And the proof is that by direct calculation, we can get this. Here you use the r factorial, or you have to find the moments. And the c may be too high, but it can be made small enough. And we'll see that we'll use this for the Johnson-Strauss theorem, right? Exponential and power law. I didn't write this down, unfortunately. Power law, well, roughly speaking, if xi are distributed as kth power, and x is the sum, the probability that x minus the expected value exceeds certain number of standard deviations of the sum is what you expect, but not for very large a. Sorry. Excuse me, I'm sorry. So I want a squared over sigma squared, not exponential. I have only k minus 2 over 2. Because I don't have higher moments, so I have only k minus 2 over 2. That also follows. You just have to compute the moments. And here you use the fact that only some moments exist. Right? All moments don't exist. Okay, that's sort of exponential. You can, again, compute the moments. Okay, I'm going to a different topic now. Basically, this topic is a dimension reduction. You'll see Johnson and Strauss and then SVD. They're both dimension reductions, right? So, raw data often represented as vectors in high dimensional space. One dimension per feature if you have feature vectors, right? This is not our job to select features and represent. We assume this has been done. Okay. Data science only worries about it as the vectors are presented, we'll say. This has been done and only deal with high dimensional vectors. It will be nice if we can reduce the number of dimensions. The overt aim is to improve efficiency, but there are other things that is useful for. Right now we look at dimension reduction as a way of getting more efficient algorithms because the number of dimensions goes down. So there are two really main methods of dimension reduction. One is random projection, like a la Johnson and Strauss and other things. This is oblivious to the data, so the projection is independent of what the data is. And we'll see, and you know Johnson and Strauss theorem, it preserves every length of a vector for a min to relative error epsilon. But you generally cannot beat epsilon about a constant. If you want to go better than that, the dimension of the projection will become very high, right? That's the usual use. So it's used extensively in theory because of A, because every vector you can show length is preserved, but B is a bottleneck for use in practice because sometimes or quite often you might want an epsilon much smaller than a constant. For example, in theory we are happy with having 1 plus epsilon times the expectation, so we are making an error of epsilon times the expectation. In practice you want to make an error commensurate with the standard deviation, which may be much smaller than the expectation. That's then this is not useful, right? So principal component analysis, or SVD, that is a property that projection length behaves well, often better than this much error, but only when averaged over all data. Some data points can project to something quite bad. With random projection, everybody behaves nicely, every individual thing behaves nicely, but here that's not so. On average, the behavior is often better. Now, the theoretical use of principal component analysis is not too many things. We'll see Gaussian mixture models, they are used there. But here's a dichotomy that's present in data science as a whole. I mean, it's arguable, you might debate that, but in theory, we use random projections a lot because we can prove theorem says every projection is bounded. In practice, perhaps I would say, arguably, SVDs use more, right? Because you gain an advantage on average, which is better. Also, SVD is what you can call data aware. The projection depends on the data. And in practice, I guess people like to use the data to figure out what to do rather than not use the data to figure out what to do. But I mean, this is just one of 10 or so controversial statements I need to make in a talk, right? So, but I don't know, maybe others coming. But we'll see both, right? we'll see Johnson-Lindner-Strauss as well as principal component analysis. I mean, if you want to make any comment, I think I'm going fast enough. If you want to make any comments, you are welcome to. And I'll also get a water break.
I hope this isn't a troll question, but is there any way to combine them to get a best of both worlds?
That's a good question. I don't know many examples where they are both used, or that is to say, at the moment I can't think of any. But yeah, maybe others can. I mean, I don't know. Yeah, it would be nice to combine them. Yeah.
So it's often faster to do so the random projections first, and then do PCA afterwards.
Yeah. Okay. So that's. So I should say that even in doing SVD, we'll see randomized algorithms. And later, David and Ken will talk about perhaps subspace embeddings, which have the flavor of random projection. So maybe that combines both in some way. Yeah. Okay, length preserving projection. So we want a random length preserving projection from D space to a much smaller dimensional space. So we'd like a matrix P, random, so that for every vector V, the length of PV is approximately the length of V. I'd like to draw your attention to one thing here which is familiar in the back of your minds perhaps, but the placement of the quantifier here is important. So I put the for all V in front of the probability. That means for each individual V, this is the probability, right? And if you want to say this for many V's, you have to take the union bound. And you have to pay in probability, right? That's good to remember. This is a contrast to, I mean, for example, we see dimensional empirical process theory where V would be inside the brackets. We cannot put V inside the brackets here, we'll see. Okay, number one. Number two, a little bit in further talks, you will see that it's useful actually not to require K to be much smaller than D, and then in fact you can move this inside. And one example of that will be subspace embeddings again, which you'll see later perhaps. Okay. So what happens if I place it inside? It's not true, right? If the quantifier is inside, K is less than D, there's always a vector V, which is in the null space of P, and PV is 0, the vector is non-zero. So of course this is false. Right? So you cannot move it inside. The other thing to remember about random projections is they do not preserve dot products. So some occasions one would like to argue dot products are preserved, but for that you cannot use this dimension reduction. Right? So that can be an issue. So original projection projected to a random k-dimensional subspace as Johnson-Lindner-Strauss in terms of matrices. P would be a random k by D matrix with orthonormal rows. But picking such a random matrix, because you have to make them orthonormal, there's dependence, it's difficult. Also arguing with them is difficult. So in fact the argument we'll give, which is based on a paper of Dasgupta and Gupta, I have a reference there, is based on Gaussian vectors rather than uniform random subspace of dimension k. So we pick IID k vectors, each with distribution normal 0 identity. This identity here is the variance covariance matrix. These are now vectors picked with standard Gaussian in each coordinate, right? That's what identity says. Okay. And we project, we use the following projection. Simply just take the dot product with each of the U's in each coordinate. See, projecting to a random k-dimensional space had dependence because the vectors were orthogonal, right? And so you had to project against each one. But now these are not, these are just independent random vectors. Okay. We'll prove that with high probability that's true. And the root k is natural. There's a root k is just a constant factor, so you can factor it out. Root k is natural because you're going because these are of length root k. The ui's are of length. No, I'm sorry. The ui's are of length root n, but there are k of them. That's why the root. So Y root k, that's that. Now u dot, so as you know, for a fixed vector v dot u is the sum of independent random variables, so it's just, it's also Gaussian distributed with this variance, right? And so here's the theorem, and the proof, this line of proof is due to Gupta, Dasgupta and Gupta. F is that projection that you took dot products with k different Gaussian vectors. There's a constant c, so I said for epsilon between 0 and 1, again not true, very, very large epsilon, the difference between the projected length, and this is scaling factor, and the real length is not very big. Okay. And you get the epsilon squared only if epsilon is between 0 and 1. And the probability is taken over all random draws of ui used to construct f. And remark, v is not random. This is for any v, right? For every, it's true for every v. And it follows from the Gaussian analysis theorem because the f's coordinates are Gaussians, right? Independent Gaussians, and its length then is the sum of chi-squareds, right? So that we use that theorem there. Now, if you want to apply it to a lot of vectors, and I'm going to go over this a little bit, in a lot of contexts, the number of vectors you apply to is polynomial, but not always. You have to be a little careful. If you want to apply to a lot of vectors, you do the union bound. So again, epsilon is this, and the projected dimension is high enough compared to the number of points, but only logarithmically. Right? We want to be n is any set of n points, then the probability that the difference of the projections is very different from the difference of the vectors is small. Okay. So every pairwise distance is preserved. And that's just by union bound. So that follows simply from theorem 1. There's nothing to do there. Okay, I'm going to show you an example where it automatically applies and an example where it doesn't. So we'll see the reasons for that. So we are given n points in RD. We want to partition into k parts so that we minimize the sum of squared distances of the points to the nearest cluster center. This is the k-means clustering problem. We're all familiar with that. Cluster center is the mean of the cluster. That's true for k-means only, right? The correct cluster center is just the average of the centroid of the points. You have to prove that. That's not true for other criteria. So find the best, so we projected this many dimensions, find the best clustering in the projection. Will this do? Since all distances are preserved to 1 plus or minus epsilon, it should do, but we need to be careful. How many distances need to be preserved, right? Crudely, the number of possible cluster centers could be, there could be 2 to the n possible subsets. Each could have a cluster center, right? And if you have to apply the union bound to that, that's not so good. That's too many. Luckily, for any m points, sum of squared distances of the mean is expressible in terms of the sum of pairwise distances. So it's enough to preserve all pairwise distances for k-means. Because everything can be expressed in terms of pairwise distances. Okay? And there aren't too many of those. There are a polynomial number of those. Here's some food for thought. How about k-median clustering, which is another clustering criterion? In that criterion, you minimize the sum of distances to the cluster centers. Now the cluster centers can be arbitrary points. So it's unclear that you can apply JL, right? Because the number of candidate distances to preserve is exponential or even infinite. So actually, when I was making these slides, I said, people will ask me if I know. So luckily nobody did, so if it can be applied. But I don't know, somebody knows the answer? I mean, can you apply a random projection to k-median? I don't know. Yeah, you have to be careful. Usually in TCS, k-median is stated as cluster center must be one of the data points. Okay. Usually in data science, it's not necessary. K means the cluster centers or centroids of clusters which need not be data points. If you assume cluster centers have to be data points, of course, then there aren't so many candidates. But if you allow arbitrary points in space, then that argument doesn't work. Now I want to show you a central and essential problem with Johnson-Linden-Strauss. Why it doesn't work in certain situations, and why, we'll see later, SVD and PCA do work. So standard mnemonic in statistics is means separated by 6 or 10 standard deviations. Okay, we want to be a little more general, so means separated by order 1 standard deviations. I want to, this is going to be a bit of a theme for a few slides, so it's good to remember. So let's say I'm given samples from an equal mixture of 2 Gaussians, normal zero identity, this is in high dimensional space, right? And the other one, the mean is mu, where the length of the separation between the means is constant. Okay, so now the standard deviation is constant in each direction, right? If I is the variance covariance matrix, standard deviation is constant in each direction, and I'm assuming the means are separated by a constant number of standard deviations. And the question is to learn what's mu, or learn the two Gaussian densities from samples. So I should draw a picture, which I'm going to draw them very close, right? And I'm given samples from this Gaussian, and we saw that they lie in a small annulus, and samples from this Gaussian. Oh, I should have drawn them different color. But your job is to separate them. Your job is to separate them and therefore learn this. Right? Now, so here's a problem with Johnson-Linden-Strauss. Random projection is no good because epsilon relative error is too high. Why is that? Because the variance in each direction is 1. The distance squared of this is about d is the dimension. The overall variance is d, so points lie at distance about d in square from the center. However, if I take this point and take its distance to the wrong center, this distance squared is d, this distance squared is constant, and when you're random, almost all angles are 90 degrees. I didn't prove it, but these two will be orthogonal essentially. And therefore, that distance squared will be d plus c. D is big. If I make epsilon error, c is lost. So, in fact, this is a very good example to remember. I sort of use this in all talks. It's a trivial example, but it's good to have in mind. If I do 2 means clustering with relative error epsilon, which is standard in TCS, you can miscluster every point, and it's still valid. Still, the objective function is 1%. Why is that? Because misclustering only costs you c, and epsilon error allows you epsilon d. Okay, that's a huge error that's allowed. So 2 means clustering is no good. I suppose I was starting to draw this picture, and I'm sorry I didn't draw that. So what is good for this? So let's see what is good for this, right? This is good for that. So I will come back to why that's good for this. But right now we want to see an intro to singular value decomposition. That's good. For those who know, I mean, many of you already know, perhaps, right? If I do SVD, there's a very nice result of M. Palin-Wang that the SVD subspace gives you this. Gives you this line joining the centers. If I now project the whole thing to the line joining the centers, then the standard deviation is still 1. Gaussian's projections give you the same standard deviation as spherical Gaussians, right? As the whole thing. Standard deviation is still 1. They are separated by c, so the points look like this, right? And that's easy to separate. You need an extra log factor if you want to get everybody right, but it's easy to separate. Provided I can find the space spanned by the centers. And the big point is that that is actually the SVD subspace. We'll see that. But first, for that, I have to recap what SVD is. And perhaps here you all, I mean, most of you know from your linear algebra what SVD is. But here's a view which is also just obvious, but is a view that's based on data, if you will, of singular value decomposition. We have n points in D space. Each row, each data point is a row of the data matrix. And SVD is just precisely is the best fit k-dimensional subspace for A for the data. So you have a bunch of data, it's a best fit k-dimensional subspace. Best fit in the sense of minimum sum of squared perpendicular distances. So another picture. So these are points in space, right? And so then I take, if I want, this is k equals 2, if I want the best plane, I do insist on subspaces, so they have to pass through the origin. Okay, bear with me on that, we'll fix that in a minute. And you take each point and take the perpendicular distance, square it and sum. The squares are very important in all of this, right? Square it and sum and minimize that over all spaces. That is the definition of SVD that I want to use. Okay. Usual definitions or in terms of matrix factorizations or what have you, but this is a natural one for data. I mean, it follows essentially from all the, we know that this to be true from the end. So equivalently, we can take the maximum sum of squares of the lengths of the projection of data points into the subspace. Here's a little picture. So here's data point AI, ith data point. Here is the subspace, which is a candidate for best fit, let's say. I could have taken sum of squares of these and minimized, or I could have taken sum of squares of these and maximized, right? Because Pythagoras says the sum of those two is a constant. Okay. So we maximize the sum of squares of the projections onto the subspace. That's a definition of SVD. Minimize. So this is just saying what I said in words. Minimizing sum of distance squares of the projections of the distances is the same as maximizing that. So you have to forget your, just as a little aside, you have to forget what least squares fit in calculus meant. There you had only two coordinates, right? And you didn't take the perpendicular distance, you took the vertical distance, right? So anyway, so this is different from least squares fit in calculus, right? In this way. Now, we least squares as well as SVD. Let me backtrack. Least squares fit in calculus doesn't have to pass through the origin, right? Depends on how the data lies. But in the SVD case, we required the subspace, so it had to pass through the origin. But that actually is no loss of generality. See later, I'm not going to show you that. But you can prove that the best fit affine subspace. If I don't insist on the origin being in it, affine subspace is the one that passes through the centroid of the data. This is just like the k-means proof. And therefore, we can translate to, we can find the centroid in the beginning, translate to make it 0, then there's no loss of generality. We're getting the best affine subspace. Yeah?
Sorry. Can you say again why is it different from least squares fit?
Yeah, okay, good point. Let's see. So what do you do in least squares is you have a bunch of points. The least squares is just two arguments, so I can draw it in the plane. I want the line that best fits, right? But how do I measure the error? I take this vertical distance. So this is the function of xi, and this is the given argument. So I take yi minus fxi squared, sum over that, and minimize. I do not take the distance perpendicular to the subspace, which is what I would do here in SVD. That's all I'm saying.
Is this like the same definition with one higher dimension or some such thing?
I'm not sure. I don't see how to fit it. I mean, yeah, possible. Yeah. I don't see how to fit it into one higher dimension. So we actually can say it's the best fit affine subspace rather than just subspace, right? Doesn't have to. Okay, so the other point we want to recap about SVD is it is probably, and this is arguable, is probably the earliest proven greedy algorithm actually working, and a very nice proof, of course. I won't go through the proof, but here's what the statement is. Here is a greedy algorithm for finding the best fit 10-dimensional subspace to the data. First, find the best fit one-dimensional subspace. That's just a line through the origin. Find the best fit line. That's sort of reminiscent of least squares, except it's measured differently, right? You find the best fit line. Then the best fit line, second time, you do the best fit line through the origin perpendicular to the first. At the ith step, you find the best fit line perpendicular to the I-1 lines you found so far. You keep going until rank of A. It's easy to see that after rank of A, it's all 0. And the big theorem, it's classical theorem, and again with a nice proof, is that for every I, the subspace spanned by the first I vectors so found is the best fit I-dimensional subspace to data. So greedy works, right? That's what it's saying. I haven't told you how to find the best fit one-dimensional subspace, and I won't tell you many methods, right? The numerical analysis has devoted a lot of time and effort to developing good methods to do that, but that's enough to do at one shot. So arguably the earliest proven greedy algorithm. Of course, I think the other greedy algorithms have been suggested before this, but in terms of proving that it works and gives you the correct answer, perhaps this is. I mean, this probably predates certainly a spanning tree and mixed vectors. Any murmurs of dissent? No.
Okay, so the greedy works if we're looking at L2 distance, right?
Yeah.
But if it were L1, then...
So, I mean, yeah, all hell breaks loose if we don't have, right, L2, or if we don't have the square. So if I measured, if I said best fit, I measure the distance rather than the squared distance of data points, perpendicular distance to the hyperplane. No, none of this works, right? Everything is dependent on the square, of course, right? And even Pythagoras depended on the square, so yeah, but it's good. Okay, so I seem to have come to the end of the first lecture. Now I can go over the entire second lecture already, or if you have questions, or we can take a little longer break, whichever. So somebody should have questions so that we can do something good with the time, right? Good.
In practice, do people do like best fit subspaces and other distance measures? And if so, how they do it?
Okay, there is some literature on other distance measures. For instance, for clustering, people have certainly considered other norms and done stuff. I mean, there is nothing as beautiful as linear algebra for other norms, but some stuff is there. Okay. And you can ask similar questions for multi-tensors, and in fact, some of this we'll see. Some of this will extend. Only briefly mention that. Yeah.
Are there results tying the case where you use L2 distances with the answers in the L1 distance sort of case? Meaning, if you solve the problem for L2 because it's easy, and the solution is not so far away from.
Okay, that's a good question. So I think your question is reminiscent of compressed sensing, right? Where we would like to minimize L infinity norm, which is not possible. Instead, you do L1 and show that under some conditions that works. Okay, so I imagine, yes, if you had assumptions as strong as compressed sensing, RIP, then it is possibly true that L2 and L1 are not so different, right? It's possible. I don't know proofs of that. So it's something that people haven't sat down and worked out, unless somebody has something to say about that. So, but the assumptions are pretty strong. We'll go over what the assumptions are, for instance, for compressed sensing, but they're strong. So under those assumptions, you can, at least L infinity and L1 work the same way, sort of, and L2 and L1 also might.
Yeah.
So this actually computes the best fit K-subspace. Is there anything more efficient if I just want to either like compute the distance or approximate the distance?
Oh, I see. Okay, so that's a good question. So in terminology here, you may want to compute only the singular values rather than the singular vectors also. Okay. It is a bit easier numerically because singular values are more stable than singular vectors. Right? Singular vectors have much more dependence on perturbations. But I don't know any direct algorithmic advantage people have taken of that to compute just the singular values rather than both.
I mean, you can use subspace embeddings if you have rectangular matrices. So if you only have the top few, things like this. Yeah.
So you can use randomized methods that will actually, you can use all the random. So, okay, sorry, David is right. So we can use randomized algorithms, we'll see. Not only in this talk, but through this several talks. And those give you singular values to some accuracy. They don't give you singular vectors. So, okay, singular vectors are notoriously discontinuous when there are ties, right? Whereas singular values are continuous always. So they give you singular values, but they don't give you singular vectors because they may be sharp discontinuous. It's good I made the talk short because we got a lot more questions then. So when we come back, I'm going to carry on with. Well, I'm tempted to do 5 minutes of this because then we'll be more relaxed at the other end. Oh, but then I have to pull up that file, which is actually. So now I won't do that. So when we come back, we'll do SVD, some randomized algorithms for linear algebra. And I want to briefly touch upon Markov chains, where I'll state the fundamental theorem as well as rapid mixing, with sort of, again, unusual proofs, different proofs, more probabilistic proofs perhaps than what one uses normally, if you're familiar with that. But I'll make it from first principles, so it'll be easy to follow.
Thanks, Ravi.
Thanks.